Both of the examples in this video are going to look at solving for equilibrium concentrations given a Kc value. This first problem here, we've got carbon monoxide reacts with water to form carbon dioxide and water. It says at a given temperature, the Kc value is 4.06. If 0.1 mole of CO, that's an initial initial amount, is mixed with 0.1 mole of H2O in a 1 liter flask and allowed to reach equilibrium, calculate the equilibrium concentrations. This is a little bit different than what we did the last day. We are going to use both an ice table and a Kc value to figure out the equilibrium concentrations. So let's set this ice table up. The first thing we want to do, as per usual, is write out our balanced chemical equation. So CO2 plus H2. And then we're going to set up our ice table. So initial concentrations is 0.1 moles in 1 liter. So that's just going to be 0.100 moles per liter of both CO and water, and 0 of CO2 and H2. The change, everything's 1-to-1 ratios. So the reactants are both going to go down by minus X. Products are both going to go up by plus X. So our equilibrium concentrations, I'm going to shorten this up a little bit just for sake of clarity. We add our I and our C columns, so that becomes 0.1 minus X for both CO and H2O, and just X for CO2 and H2. Now this is where these problems differ. We do not have an equilibrium concentration of either a reactant or a product, but we do know what the Kc is. So we can write an equilibrium expression for our Kc and then use our Kc to solve for X. So our Kc is going to be CO2 times H2 divided by CO and H2O. So remember, all of these concentrations in our Kc are at equilibrium. That means that we are inserting this row into our Kc expression to solve for X. Problem told us Kc was 4.06. We know that CO2 and H2 are both X. And we know that CO is 0.1 minus X, and so is water. This is going to simplify to them 4.06 equals X squared over 0.1 minus X squared. From here, simple math. We're going to take square root of both sides. So that gives us I'm just going to keep 4 decimal places, 2.0149 over X divided by 0.1 minus X. We're going to multiply both sides by 0.1 minus X, which is going to leave us with 0.20149 minus 2.0149. X is equal to X. Okay, so if we solve this, I'm going to let you do the math on your own. You should get 0.0668. So now that we know X, we can put those back into our equilibrium expressions to figure out what the equilibrium concentrations are going to be. So we know that CO and H2O are both 0.1 minus X. So at equilibrium, let's put in our EQs here. It's going to be 0.100 minus 0.0668. So those are going to be 0.033 moles per decimeter cubed. And then CO2 at equilibrium is the same as H2 at equilibrium. Those are just X, so they are going to be 0.0668, or let's just round it to 0.067 moles per decimeter cubed. That first problem worked out really nicely because we ended up with perfect squares, so it was very easy to take the square root of both sides in order to solve for X. It's not always going to turn out so easy. So this problem here, we've got hydrogen and iodine are placed in a container, and they're going to react to produce hydrogen iodide, so 2HI. And then let's just take our information from our problem and start setting up our ice table. So it says we've got a K, and then determine all the concentrations at equilibrium if 4 moles of hydrogen, 2 moles of iodine are placed in a 2-liter flask. So the concentration of hydrogen is going to be 4 divided by 2, or 2.00 initially. Our iodine is 2 divided by 2, so that's going to be 1.00, and our HI is 0. Our H2 and our I2 are both going down by negative x. Our HI is going up by plus 2x. So just to simplify things a little bit, our H2 is 2 minus x, our I2 is 1 minus x, and our HI is 2x. So again, we're going to set up a K expression because we don't have one of these equilibrium concentrations, but we do have our K. So our Kc is going to be equal to HI squared over H2 times I2. So we know 49.7 is going to equal 2x all squared divided by 2 minus x times 1 minus x. So let's just simplify things out a little bit here. So that's 4x squared, and if we expand the denominator, that's going to become 2 minus 3x plus x squared. I'm going to let you do the math here, but what we want to do is set this up to look like a quadratic equation, so something that's going to be equal to 0. So I got 45.7 x squared minus 149.1x plus 99.4 is equal to 0. From here, we want to use our quadratic equation. So remember, quadratic equation is negative b plus or minus the square root b squared minus 4ac all over 2a. So let's plug in our numbers. We've got x equals, let's go back to a normal color here, negative b, so negative 149.1 plus or minus square root of negative 149.1 squared minus 4 times 45.7 times 99.4 all over 2 times 45.7. So if we were to solve this, we get 149.1 plus or minus 63.72, all divided by 91.4. So we're going to have two solutions. We need to look at both the positive and the negative solution. So if we look at 149.1 plus 63.72 divided by 91.4, we would get 2.328. Do that math on your own. Make sure that works for you. If we do 149.1 minus 63.72 divided by 91.4, we get 0.934. The challenge here comes from which of these is the correct solution. So what you need to do is look at each solution, put it back in your equilibrium concentrations, and see if it works. if we take this one here, the 2.328, and we put that back into our H2 concentration at equilibrium, we would have 2.00 minus 2.328. That would give us a negative concentration. Okay? That does not work. We cannot have a negative concentration. So our solution is that X is going to be 0.934. From here, it's the same as the last problem. So we're going to solve for each of those equilibrium concentrations. So H2 is 2.00 minus X, which was 0.934, gives us 1.07 moles per decimeter cubed. Concentration of I2 was 1.00 minus X, so minus 0.934, gives us 0.07 moles per decimeter cubed. And lastly, HI at equilibrium is 2 times X, so 2 times 0.934, gives us 1.87 moles per decimeter cubed.